All right. Hi, everyone. Thanks for joining us today. And Evan Schwab is going to be our speaker, and he will begin in just a few minutes as attendees are continuing to join the session. And as a quick reminder, a brief survey will follow at the end of the session. And please share your moments of the virtual conference on social media, Facebook or Twitter, using the hashtag ODSC virtual. And we have 30 prizes to give away today. And your feedback is going to help us shape future conferences, and we love data too. And yeah, and we can get started.
Okay, thank you for the introduction. So hello everyone, my name is Evan Schwab, and thank you for attending my talk. I am a research scientist at Philips Research North America, and we are headquartered in Cambridge, Massachusetts, so just a stone's throw away from where the Open Data Science Conference was going to be held in Boston. So as the title of my talk suggests, I will touch on two main themes. One is, One is explainable AI. So what does this mean and who are we explaining it to? And I'll also touch upon the state of the art in this area. And the second theme is weakly annotated data. So what are the types of ground truth annotations that are usually used in supervised machine learning? And what does it mean to be a weak annotation? So these two themes are important for addressing certain issues in moving machine learning models out of the lab and deploying into a real world setting. And this is especially important for our industry at Philips, which is healthcare. So Philips is a leading health technology company focused on improving people's health and enabling better outcomes across the health continuum, from healthy living and prevention to diagnosis, treatment, and home care. This includes personal health related to sleep, dental, grooming, and respiratory care, then diagnosis and treatment related to image-guided therapies from imaging systems like ultrasound, X-ray, MRI, CT, and others. And also connected care, such as patient monitoring, healthcare informatics, and population and genetics health. And my team and I work on improving clinical workflows for radiologists, from scheduling, prep, and image acquisition to data interpretation, reporting, treatment, and follow-ups. And in particular, we are interested in integrating AI to assist radiologists in their clinical workflow to ultimately provide improved patient outcomes. And my interests are specifically in applying deep learning and computer vision to automatically analyze these medical images. So to outline my talk, I'll begin with a brief introduction of the tasks of computer vision. Then I will give another overview of our two themes, which were annotations and explainability as they relate to medical imaging data. And then I will describe our clinical use cases for using AI in radiology. And I will then get to the meat of our presentation, which will be our methodology for detecting critical findings in chest X-ray using weak annotations. And I will end with some experimental results on data from multiple hospitals. So in computer vision, we are interested in using machine learning or deep learning to automatically analyze images, for example, by automatically classifying the contents of an image, automatically detecting the location of different objects in the image, or even outlining or segmenting specific shapes of objects and images. We are interested in solving similar tasks in the case for medical images, by classifying images as being positive or negative for a certain disease or pathology, detecting or localizing findings in images, and segmenting disease structures or parts of the anatomy in order to help radiologists perform diagnostic measurements. However, there are some stark differences between computer vision for natural images and for medical images. So for a comparison, I have done a simple Google image search for cats and also for chest X-ray images. And so a great number of computer vision deep learning algorithms have been matured on data sets of natural images like ImageNet, one reason being the enormous availability from public sources such as Google. And Not only are the images available, but ground truth labels for supervised machine learning are relatively inexpensive to generate because of the layman familiarity of everyday objects. There are resources available to crowdsource the labeling of these natural images, which can be done with great accuracy and consistency by almost anyone. Alternatively, in the medical domain, this is not the case. For training of deep learning algorithms, we are hindered largely by two things. One is the lack of available data, which is due to government and hospital regulations, privacy laws, and also the sheer expense of acquiring certain data. And two is the lack of ground truth labels, which is due to the fact that labeling is very expensive because it requires a consensus of medical professionals to diagnose difficult findings that takes years and years of experience. And you might notice some differences with the images themselves. So for images of cats, we have different colors, positions, poses, locations, and even cats that are occluded by things in the foreground or background. And you might think, oh, if we just look at these chest x-rays, it could be a lot easier to classify because there's less variability. But there's less variability in the anatomy. But what we have is variability in the disease pathology, which can embody different locations, occlusions, positions, and different textures. So this is equally as hard. In this talk, we will cover the two fundamental issues, as we mentioned, the lack of ground truth labels and a heightened need for explainability or interpretability of our algorithms. Since the medical domain is concerned with life or death diagnoses, both accuracy and explainability are vital for real-world adoption and trust of deep learning algorithms into the clinical practice. For example, if we look at the image on the left of a sample of chest x-rays, a radiologist may not be satisfied with an image level prediction of mass or pneumonia or cardiomegaly and may want a further explanation in order to trust the output of the algorithm, such as a bounding box localization of where the finding is that we can see in red. So in this sense, I regard explainability not only with respect to the end user, which is the radiologist, but it also benefits the deep learning developers to better understand what the algorithms are actually learning and overcome this idea of working with black boxes. So to be more precise about this relationship between explainability and labels, we take a look at the hierarchy of labels required for classification, object detection, and segmentation using supervised deep learning. On the left, we have image level labels, which predict a class to describe what is contained in the image. These are more inexpensive to acquire because the labeler does not have to draw any detailed annotations. However, it may be the least explainable because the subtlety of the finding may be hidden, unlike a classification of a dog or cat, which anyone can find in an image. In the middle are bounding box labels, and these are encoded by real number, XY location coordinates, and the height and width of the box. And these become more expensive to label, but provide additional explanation for the detection of critical finding. And finally, on the right are images that have pixel level labels for segmentation, where we may not only want to detect an object, but we may want to provide additional diagnostic measurements like the area of a lesion or the diameter. And this is the most explainable, but comes at a much higher cost for such detailed annotation. I also want to share an alternative illustration of this relationship and define weak annotations or weakly supervised problems. And this slide is courtesy of another company, Tencent AI, who gave a lovely talk recently at the International Symposium on Biomedical Imaging. And this is a diagram of a great explanation of the differences of weak supervision. So as we outlined previously, we have three main types of computer vision tasks on the y-axis. We have classification, detection, and segmentation. And we have three different types of labels on the x-axis, which are image level label, a bounding box, or a pixel label. And so the center line in blue here demonstrates most standard supervised learning problems. Where we want to perform image classification, we require the image labels. If we want to do object detection, we require the bounding box. If we want to do segmentation, we require the pixel level labels. But above the blue line in this yellow region is known as weak supervision. So where we encounter problems such as this, where the blue star is, where we want to do object detection, but only have image labels. And similarly, we may want to do segmentation and only have image labels, or segmentation only have bounding box labels. So these situations arise when the labels are too expensive to generate, but there are methods to overcome this difficulty without having to manually generate more annotations. And some of these methods are outlined in the flow chart on the left-hand side for cases where we have limited labels. For instance, semi-supervised techniques use a small subset of manually labeled data to automatically generate more labeled data in an iterative way. And there are also many methods for transfer learning or domain adaptation, which reuse models that were learned on labeled data and try to transfer it to new data that does not have labels. But we will be working with another type of weakly supervised method that attempts to break down the data into smaller parts and learn labels for these smaller parts. And we will also not discuss anything about strong supervision, which was the theme of the talk from Tencent AI. So now I'll move on to our application area, which is radiology, and some of the clinical use cases for AI. In the current work, we deal with chest x-rays because they are one of the most common types of medical imaging exams for preliminary diagnosis, especially in the emergency department. And chest x-rays are one of the most frequently performed procedures because they are fast, non-invasive, have low radiation, and are relatively inexpensive compared to other medical imaging exams. In addition, they provide a diagnosis of many critical abnormalities related to the heart, lungs, and bones. While experienced radiologists are very good at reading and diagnosing chest x-rays, there are many ways that AI can be used to assist and better optimize their radiological workflow, and therefore decrease the burdensome load that frequently leads to burnout. So this includes such areas as prioritizing radiology work lists, calibrating severity between different radiologists, triggering follow-up alerts, and alerting to incidental findings. And because chest x-rays are so frequently utilized, we've been able to access a very large data set from the Beth Israel Deaconess Medical Center in Boston, Massachusetts, and also in partnership with MIT, of a data set of around 350,000 chest x-ray images. But as expected, these images do not come with any labels. However, they are accompanied with the radiology reports, which were written during the acquisition of those images. And these include a discussion of the findings and impressions of the images. So using natural language processing methods, it is very possible to automatically obtain image level labels from the text. However, information related to any type of localization is a bit harder to obtain, and especially labels like bounding boxes or pixel level labels. So the goal of this work is to automatically classify and localize critical findings in chest x-ray, trained only using image level labels and no ground truth annotations. And this is a weakly labeled supervised learning problem. And we will present our recently published work at the International Symposium on Biomedical Imaging, which is using a weakly supervised method known as multi-instance learning. But before getting into that, I want to catch everyone up on the state of the art in deep learning. And so as we're all familiar, given an image level label, convolutional neural networks, or CNNs, do very well for image classification. But they do not provide any localization. They additionally don't provide any explanation of why the CNN gave the classification it did. So the output is simply a score or probability in the case of binary classification, of having the disease or not. And we can then threshold that score to give a 0 or 1 prediction of the disease. So here I have an example of a normal chest X-ray with no finding, with a very small score of 0.05, and a chest X-ray with pneumothorax, which gives a score of 0.91. Right. So what has been done in the area of explainability is the recent groups of works that have been devised that better explain the reason for the given classification of a CNN. And these are broadly known as saliency methods. And commonly known methods such as gradient class activation mapping or grad-cam essentially provide a way to look under the hood of a deep learning model and identify the important weights, the learned weights of the network, and then project them back as heat maps onto the original image to interpret the model. However, there are a few notable downsides to this general method. One is that it is post hoc analysis, meaning that the heat map is not tied into the optimization of the model during training, and therefore results may show correct classification but incorrect localization, and there's no natural mechanism to improve the result. Some works, however, try to solve this by incorporating the heat map results back into the optimization in a two-step method that takes a thresholded region of interest in the heat map and then puts this through its own smaller CNN and combines the result of the full image and the region of interest to classify the image. But one downside is that it's not end-to-end, meaning that we have to train step 1 first in order to generate the heat maps that are needed for step 2. And therefore, step 2 could suffer if the results of step 1 are not accurate. Secondly, if we look at the dimensions of the image input here in red and the dimensions of the output heat map, we see that the heat map is of size 7 by 7. It's a small filter at the end of the network. And the original size of the image is 224 by 224. So they are upscaling this from 7 by 7 to 224 by 224, and therefore it can suffer from sometimes large and blurry localization results, as can be seen in some of these examples. So actually, I want to be able to do an animation. Can you still see my screen?
Yes.
You can. You can see my my slides now. Going through
Yes.
animation.
Not the animation.
Oh. Can I share my whole screen instead of just the application? Sorry for the delay. Okay, I'll just go through it without the animation then. So to give you a better idea of the relative scales of these grad-cam methods, consider this full resolution chest X-ray image of size 1024 by 1024. And what I'm going to show is that all images are drawn to scale. And in fact, unlike natural images, medical images are usually taken at very high resolutions, even on the order of 3000 by 3000 pixels. And so this is in order to also to read some of the subtleties of some of the disease pathologies. So training CNNs on this size of an image is usually computationally expensive. And also, rather than training from scratch, the usual approach is to utilize transfer learning with weights pre-trained on a different data set, sometimes ImageNet. So the very first step is to downscale the full resolution image to something appropriate for the pre-trained network. So in this case, 224 by 224. Then through grad-cam, the weights of these filters are then predicted, and we are upscaling them back to size 224 by 224. So we can see why it's a blurry heat map localization. So instead of this regime, consider that we maintain the full resolution image and instead take an image patch of the size 224 by 224 and feed this into the pre-trained network. And we can repeat for a number of image patches and predict if the critical finding is in the patch or not. But again, we don't have the labels for these patches, only the image label. So the major question becomes, how do we relate the image class prediction with the patch class prediction? And in addition, as a bonus, once we have a network in place, we can also apply grad-cam to each one of these patches to get a finer grained pixel-wise localization of the critical finding. So the question of how to build a network to relate the patch-wise predictions with the image level class label is answered by a machine learning method known as multi-instance learning. And so as a toy example, consider these three sets of keys. We have global information or binary labels, which say that the first set cannot enter the secret room. The second set can enter the secret room, and the third set can also enter the secret room. So the question is, which individual key is the one that can open the secret room? As humans, we are quite good at reasoning the logic, and I don't have to put a poll out there, but we can easily see that it's the green key. And why is that? It's because it's contained in the two sets that can open the door and is absent from the set that cannot open the door. Therefore, we have detected the local information or instances that are responsible for the class label. And I think we can all agree that identifying which key is responsible for opening the door is more explainable to a user than just being able to classify which keychains open the door. The same technique can be applied to images, where instead of individual keys, we create local patches of the image as instances and ask the same question: which patches are responsible for the differences in class? So here's another toy example. We have two classes of black and white images of different shapes. We have circles, triangles, squares, and diamonds. And multi-instance learning method breaks these images into smaller patches and uses these to learn a classifier of the images. The method automatically learns that the discriminative patches contain triangles for class 1 and circles for class 2, while the non-discriminative patches are those that the two classes have in common, which is the black background and the circle shapes and the diamonds. We not only can accurately classify the images, but now we have the reason for their class assignment, and this is explainable. Likewise, the same can be done for medical images, where in this example, we again have two classes, critical finding and no critical finding, and we ask which patches are discriminative, i.e. which patches contain the critical finding and which patches are non-discriminative or of the normal anatomy. So using this framework, where we extract patches from the image, we can then feed them into a pre-trained network, and the output will be a score of predicting pneumothorax versus no pneumothorax, for example. But since we don't have labels for each patch, we take the patch with the maximum score and use this in our loss function with the full image label. And so the max, it's a max pooling layer, which is the last layer in the end-to-end network. And so the optimization drives the scores of the individual patches. Thereby simultaneously, we classify the image and we localize the critical finding by visualizing the patches with very high scores. And then, for instance, for subjects with no critical finding, the optimization will drive the max patch score towards towards 0. Therefore, no patches will indicate locations of critical findings. So on the right, I show how we chose our patches We took an 8x8 grid of overlapping patches with a stride of half the patch length. So in the green is one patch, and the pink is each of the stride of that patch. And each patch will have a predicted score at the end of between 0 to 1, where we visualize by thickness and color. So patches with 0 will be very thin white patches, and patches close to 1 will be very thick dark red patches. And in this example on the right, there is one patch that is highlighted most, which correctly identified the pneumothorax, which is given with this red segmentation. And as an example, it has a score of 0.83. So that score is also then the score of the image class. So on the next slide, I'll show that we're not the first, obviously, to apply multi-instance learning on medical data. Multi-instance learning has been around for a few decades now in machine learning, and then more recently in deep learning, and more recently too in the medical domain. And we got the inspiration from a multitude of weekly supervised works in the past few years, which span mammography, brain MRI, whole body CT, digital pathology, microscopy, and more. So these are all cases in which the needed ground truth annotations are too expensive to obtain. So next I'll show results on our method on chest X-ray classification and localization, where we completed 3 experiments on 3 different data sets, each containing a different critical finding: pneumothorax, pneumonia, and pulmonary edema. So the first experiment is on data acquired from the University of Washington Medical Center. It's a binary classification experiment between subjects with no findings and the critical finding of pneumothorax. So this is the first table above. And we compare multi-instance learning with 2 other state-of-the-art approaches: a traditional CNN that trains on image class labels and predicts image classification only, a UNet that trains on image and pixel class labels and predicts an image classification and segmentation, and our proposed multi-instance learning, which trains on only image class labels and predicts both an image class and bounding box localization. And these methods are comparable because we have chosen the same CNN architecture backbone for each method. And we report the AUCs there, which was an average over 5-fold cross-validation. We can see that the CNN does outperform on its one task of classification, but it provides no localization information. And our multi-instance learning provides both and also outperforms the UNet, which had required expensive pixel labels like the image here, the segmentation in green. The second and third experiments are shown on the bottom table, where we can scale this approach to pneumonia from the publicly available RSNA Kaggle Challenge dataset. And this one actually contains ground truth bounding boxes, but these were not used in our training. And secondly, pulmonary edema from the MIMIC CXR dataset from Beth Israel Deaconess Medical Center and MIT. And we can see both relatively good AUC classifications in the 80s. So these are quantitative results for classification, but I will next show qualitative results on the critical finding. So again, yeah, we used overlapping patches with a stride of half the patch size. The faint red blobs that you see are the ground truth pneumothorax segmentations that we manually annotated. And the dark red patches indicate high scores near 1, while faint white patches indicate low scores near 0. And you can see that our method is very good at localizing the critical finding with various shapes, various sizes, and even in multiple locations as seen down here. Lastly, we also include an image, an example of an image without a critical finding. And so you see barely any patches on here because they are all very close to 0. You can see some very faint white patches. And so that correctly classified the image with a low score. Yes, all of the patches were driven down to 0. Next are similar results on pneumonia. And the ground truth bounding boxes are shown in either green or faint blue. And we can see a great alignment of our patches to the ground truth and also for multiple regions as seen in these two images here. And then finally, results on pulmonary edema. And this data actually did not have any ground truth annotations, but we can see a consistency between the resulting patches on the lower ends of the lungs. And we were able to verify the accuracy of this with a radiologist from the Beth Israel Deaconess Medical Center. So I just want to conclude. Our multi-instance learning method enjoys a number of applicable features. It jointly classifies and localizes critical findings in an image. It does not require local annotations, which are expensive to obtain. And it is an interpretable end-to-end deep network. As we saw, it's also scalable to any critical finding or maybe even general abnormalities so that we don't have to train we don't have to annotate for each different critical finding. And finally, because it's powered by CNN, at the patch level, it can be extended in a number of ways, not only from binary classification, but multi-class problems, regression problems, where we're interested in severity estimation, patch-wise saliency methods like grad-cam, like I said, or perhaps other types of segmentation or feature representations like autoencoders. And finally, it could be applied to other modalities, as we've seen with some of the example works from other groups. And for instance, could be scaled to 3D, where we could use 3D patch CNNs or even use the slices of our volumes instead of patches. And so, yep, to conclude, I would like to acknowledge our collaborators at MIT, Beth Israel, University of Washington Medical Center, and my colleagues at Philips who made this work possible. And just so you know, this is a rendering of our new North America headquarters that was just built this year in Cambridge, Massachusetts. It was just completed. And we were there for 1 month or 1 or 2 months before we had to work from home. So hopefully we'll be enjoying that area again in the coming warm weather. So thank you for your time, and I'm happy to take any questions. So I'm looking at the okay, so I see one question here in the questions area. In the real world, do you usually see such a balanced data set, referring to the 500 and positive and 500 negative examples? How does your metric and approach change? So it's important to have a balanced data set always for these types of deep learning experiments. We chose 500 and 500 because this is a relatively very small number, and this was because this was the amount of manually segmented pneumothorax cases that we were able to obtain. So we wanted to verify at the end with a fair comparison that our method was actually finding what it was supposed to be finding. And so that's why it has just that amount. So in the future, obviously, the robustness of our algorithm and results of AUC would, I would expect, increase when we go to increase the number of training samples. Let's see, we have another question. Did you use intersection over union metrics? Not yet. So that's a great question. Maybe I can go back to one of these pictures here. Yeah, intersection over union metrics is a way to quantify how well your localization result was. The difference here is that when doing a traditional detection prediction, we would output a bounding box, which is parameterized by the XY coordinates and the height and width. So if we're outputting one or more bounding boxes, we could easily compare intersection over union by taking the difference of those coordinates, essentially. But ours, we have a number of boxes that were just given by given by our choice of size. So they're not necessarily so it's not clear how to do this in a standard way because we have so many different boxes. So we could think of a number of ways where we might take each of the patches and see the overlap with the ground truth area, or we could take the union of all of our patches, or this might require thresholding only patches of a certain score over 0.5, let's say. So we haven't figured out a good way to do that. Also a way that would be comparable to other methods in a way that is akin to the intersection over union metrics that might be used in some of the Kaggle challenges. So yeah, this is definitely future work where we want to quantify the localization error with respect to both bounding boxes and, as we've seen, actual segmentations. That's a great question. Another question. Does image label mean each slice has a positive or negative status? Image label. Well, slice here, I'm not sure what you mean by slice. These are two-dimensional images. But if we're talking about the patches, so does image label mean that each patch has a positive or negative status? No. So the only thing that we know is that if your image label has a positive label, that means that at least one of the patches must have a positive label in that image. And in the case of a negative label image, we know for certain that none of the patches in the image will be labeled positive. So the algorithm uses this information in order to come up with its results. But at the onset, we don't know anything more about the patch labels themselves. Another question, what do you think are the next steps for explainable AI in medicine? Yep, thank you for that. That's very broad also. Yeah, I think explainable means in the medical sense that the clinician must trust the algorithm. So providing just a number or a score and not understanding why. I've heard in some cases that this actually could even prolong the job of the radiologist so that they might then question their own judgment and have to spend more time reconciling the output of an AI algorithm and their own experience. So I think, yeah, more needs to be done with sort of explainability in terms of detection of these objects. So have you or others considered active learning or weak supervised learning to overcome the paucity of labeled data? Yeah, active learning is another great area, and I think is especially useful in the medical domain. Active learning would be in the case where we can actively select new cases to add to our training set that we know would basically enhance the accuracy of our model. I also think in that vein, I think continual learning, which there was another presentation in this conference, is really interesting for the medical domain because we always do have the human in the loop which is the radiologist. So we're not replacing the radiologist, but if they could provide their input, which is naturally part of their job, and this way can update the results of the algorithm and continuously improve it, and also in an active way where we need to know which examples are good to include and which are not good to include as we update the model. I think these are both also should be part of the future of AI in medicine and in also explainable AI. A few more questions. I don't know how much we are on time, but what happens when discriminating visual features are much smaller than patch sizes and are diffuse, present throughout the image? That's a great question too. At least for diffuse, we have seen results where it's able to find different size pathologies. So we've also seen different sizes, but if it's smaller than the patch, so we have chosen from the beginning a patch size, which was just easy because it was the size of the pre-trained network. But we could imagine extending this to multi-scale, or there are ways to do what they call multi-instance learning. So let's say we have a patch that's identified positively. We could divide that into smaller patches to get an even finer grain. Or as I mentioned before, using grad-cam is another way to get a finer detail within the patches. So there could be different avenues to make it finer, smaller patches or different size patches, for instance. That's a great question. So how did you, next question is, how did you quantify accuracy of your bounding boxes? And I mentioned that before. There was another question about that related to intersection over union, related to a ground truth bounding box. And we haven't done that yet. So that's the next step to do. And there could be a number of interesting ways to look at it. Given that we have all these different patches, we might determine the number of overlaps with the ground truth to quantify. But I think the important part is to somehow relate it back to a standard way of quantifying. Because if we come up with our own quantification, it might be hard to relate that to a UNet segmentation algorithm. So I think it's important to come up with a standardized way to do that. We have some longer questions. Let's see here. Was there one experiment where the model was discriminating between negative pneumothorax, pneumonia, pulmonary edema? Or are these three separate models where you're discriminating between a positive or negative? Yes, so it's the latter. So what we did here was just 3 binary experiments of yes or no for the disease or not. One thing that's very possible that I mentioned at the end was that we could transform this into a multi-class, so that each patch, instead of a 1 score, it has multiple scores. And this has been done on different other works where they want to classify different parts of the anatomy, where maybe 2 parts of the anatomy can be co-present in the same area. This can be true for certain pathologies where you could have a comorbidity. So we could extend that to a multi-class scenario in a similar way. And then maybe one final question. Oh, yes?
Yeah, one final question.
Okay. It says, in the real world, if the data is imbalanced and the real positives are a small percentage of the total, you'd get a higher AUC by predicting more true negatives, right? However, it wouldn't be as useful in identifying the true positives. How do you manage recall in that case, assuming imbalanced real world training? Well, that would have to be the same way that this would be no different to try to battle imbalance here. But just to be clear, there isn't an imbalance on the patch level. The imbalance would be only on the image level. So it would be the same type of, nothing new here. We would tackle it the same way as you would other imbalance problems. So I think that's it for the questions. Okay.
Yeah. Thank you, speaker Evan Schwab, and thank you for all the attendees who come to this session. And please complete the first survey at the end of the session for us to help with future conferences. And yeah, thank you, everyone.
Thank you. Thank you, everyone. Goodbye.